Good morning and welcome back to the course of microwave engineering. So if we recall from our previous lecture, we studied the reflect klystron oscillator circuit in which we utilize a single cavity to produce the sustained oscillation in order to generate the microwave frequency. There we derived the derivation for bunching factor and also the operating mode of the reflect klystron. We saw that is the fundamental operating mode of reflect klystron we are going to get at the interval 1 and 3/4 cycle. So after studying the reflect klystron, which is essentially acting as an oscillator circuit for the microwave engineering, we will go ahead for the another type of linear beam tube, and that is a traveling wave tube. So let us go and discuss the topic traveling wave tube. This is another linear beam of an electron tube which is used essentially for the amplification of the micro signal, similar to two cavity klystron amplifier. But the change over here is that this particular traveling wave tube is not going to employ any kind of a resonant circuit, but instead it makes use of a special structure called as a slow wave structure in order to produce the velocity modulation effect. If you recall, in the two cavity klystron amplifier, the velocity modulation was exercised by making use of two separate cavities, buncher cavity and catcher cavity, right? And the electron interaction was taking place over a very limited region in the case of two cavity klystron amplifier, and that is limited to the only the width of that small narrow gap of the buncher cavity. On the other hand, the next type of microwave linear tube that we are going to see, we call it as a traveling wave tube amplifier. We see that the continuous interaction of an electron beam will take place with the microwave signal, and here the much more higher amplitude of the amplification of the microwave signal can be easily achieved. And this next type of tube is going to provide us a greater amount of amplification over the broad range of a frequency spectrum also, and that's why traveling wave tube amplifiers are popularly known as broadband amplifiers of the microwave signal. So let us go ahead and let us see how typically the construction of this particular tube will look like, and we will go to the working principle, and there afterwards we will see the application. So here the traveling wave tube amplifier. The traveling wave tube amplifier, it makes use of a special type of a structure. This type of amplifier in the form of a linear beam tube was originally invented by Kompner in 1944. Now this traveling wave tube amplifier find its application especially in broadband amplifier of the RF system. So first of all, in order to understand the basic working principle of a traveling wave tube amplifier, we should know the differences between the two cavity klystron which we already studied, which is acting as a amplifier, and this type of a tube. So a brief distinguishing feature between the two cavity klystron and traveling wave tubes are specified over here. So here there is a two different classification of the tubes. Both these tubes are acting as a microwave amplifier circuits, but still they are different. So some of the few distinguishing parameters are listed out over here. So one by one we will study the difference between the klystron and traveling wave tube. First of all, the first point of differentiating is in klystron we essentially make use of resonating circuit, right? So klystron make use of resonant cavity circuit. On the other hand, if we compare the operation of traveling wave tube, it is totally non-resonant circuit, right? So the broadband operation of the traveling wave tube is hidden over here. As being it is non-resonant in the operation, this traveling wave tube amplifier can be used to amplify large broadband microwave signal. So that's why the amplification can be controlled over a broad range of a frequency rather than amplifying a particular frequency component of the microwave that normally happens with the klystrons. So the next distinguishing parameter is, in the case of klystrons, we already saw that the interaction is going to occur over a very narrow tube gap. We saw that there are two separate cavities are located, and these cavities do possess certain gap. So if you recall that particular gap, that time we denoted with small letter d. So this particular gap is very small, and hence there is no scope for the electron beam to get interacted with the microwave signal for the longer period of time. On the other hand, if we compare the operation of a traveling wave tube, the interaction is going to occur with the electron beam over a larger length of the tube, and that's why larger amount of amplification is easily possible when we make use of traveling wave tube. The third main difference between the klystron and the traveling wave tube is, in the case of klystron amplifier, the wave, that is a microwave, which is interacting with the beam of electron, it is not actually propagating. As the interaction is limited over a very narrow region of the cavity gap, essentially the wave, the RF signal, in the case of klystron amplifier, is not traveling at all. On the other hand, we will say that in traveling wave tube, the micro signal which we want to amplify by making use of electron modulation process, so that electron modulation process will actually support actual propagation of the micro signal along its axial direction. So here, that's why the name is given traveling wave. So here the micro signal which we want to amplify is actually traveling along the axial direction of this particular tube structure, and upon traveling it continuously interacts with the electrons, and the electrons and the electron beam with the microwave signal. In order to cause the interaction, we are going to make use of a special structure. This special structure we call it as a slow wave structure, right? So the next thing over here is the traveling wave tube, as it makes use of helix type of a structure, or it is a coil like of a structure. It is a non-resonant in operation. The electron beam from the cathode is continuously interacting with the axial RF input field over a longer distance inside this slow wave structure, where both velocity and density modulation of the electron beam is going to occur. Now the schematic of traveling wave tube amplifier is shown over here, the physical construction of it. So as usual, we should have a source of an electron, and the source of electron will be provided by making use of a cathode. As usual, the DC applied voltages are skipped in this particular diagram, but it is assumed to be there. So the cathode, when it is get sufficiently heated by applying a negative potential over here, so here is the cathode. Now this cathode we are going to heat by means of applying a strong DC negative voltage, so that the cathode will start emitting electron. So these electron will form an electron beam, and a beam we are going to get over here. So this pink color, whatever we have shown over here, this is an electron beam, right? In the tube structure here, if you notice, I denote with a different color. This particular section where I am encircling with the blue color is a helical structure, and this we call it as a slow wave structure. This we call slow wave structure. This slow wave structure is a main part of the operation of this traveling wave tube amplifier. Okay, so this slow wave structure is intended in order to slow down the electrons in order to interact them with the input microwave signal. The microwave signal which we want to amplify is given as input from here. The microwave signal is supposed to have a smaller magnitude. Now this microwave signal is input over this slow wave structure, and the electron beam is passing over to the slow wave structure. Now the slow wave structure is made in a such a way that it will resist the path of propagation of the electrons purposely. So that's why the wave or the electron, when they travel over this slow wave structure, the velocity of these electrons in the electron beam will get modulated. Okay, and when the velocity of the electrons get modulated, the electron will transfer their energy to the input microwave signal. So the microwave signal which we want to amplify is given over here as an input. Okay, so the interaction of the microwave with the electrons in the electron beam over a continuous path is going to occur in the given slow wave structure, right? And when we take out this microwave signal at the output, we will find that this microwave signal will appear amplified in the output, and thus we say that the applied microwave signal gets amplified, right? So this is a simple principle working of the traveling wave tube amplifier. The electron beam is also focused axially by applying external static magnetic field, which are not shown over here, but it is assumed to be present. The micro signal which is injected on the helix slow wave structure, the helix slow wave structure, we will see in detail what it consists of. It is nothing but a coil like structure which is purposely made zigzag or in order to resist the flow of propagation of electrons. Okay, so this slow wave structure can be constructed by a variety of different geometries that we will see later on. The micro signal which is injected over this slow wave structure, it surrounds the electron beam, and this provides the axial component of the signal wave that interacts with the electron beam. The DC beam voltage which is applied to the cathode is adjusted so that the beam velocity is slightly greater than the axial electron beam component, right? So during the transit along the axial direction, the electron beam is going to transfer the energy through the traveling wave. So here there are two different types of waves. One is the wave, or we call it as a space charge, which is developed by the beam of electron, and another is essentially a traveling wave. So the traveling wave is nothing but the microwave signal which is traveling over the slow wave structure. Now when the microwave signals start traveling over the slow wave structure, it induces the axial field in this particular direction, which is exactly in a linear direction with the beam, which is shown over here. Okay, so this red color arrow, whatever I am showing, we call it as a axial electric field. This is an axial electric field, and this field will get generated when we inject the microwave signal over the slow wave structure. This axial electric field will start propagating in the same direction of the beam of electrons, and thus it will continuously interact with the beam of electron over the slow wave structure, right? Now here there is also an attenuator system which we are normally going to place somewhere over here at the middle of this slow wave structure. Now this attenuator circuit is essential in order to nullify the effect of any particular reflection that could take place during the operation. Okay, so for time being, for the simplicity, the attenuator circuit or the attenuator part is neglected over here to show. Okay, so the losses in the system that may get caused because of the energy transfer from the electrons, that can be appeared at the output of the helix, right? And as the attenuator is placed over the part of the helix near the output end to attenuate any reflected waves due to the impedance mismatch that can occur during the process, the attenuator is adjusted such that sufficient length of interaction region so that the attenuation, whatever it will cause to the amplified signal, we can neglect it, because it will become insignificant when it is compared to the amplification amount of the signal, right? So the next figure, whatever it shows, is some of the industrial and commercial available traveling wave tube amplifiers. So these are typical the diagrams of actual commercial and industrial traveling wave tubes available in the industry and which are essentially used to amplify the microwave signal at a very high frequency. Okay, and the detailed operation how the amplification of the microwave signal take place in a traveling wave tube is explained over using this block diagram. Now here we observe the entire operation. So the cathode we find on the left hand side over here. This is a cathode. This cathode is applied with a DC electric field. Now this DC electric field is a V0, right? So when the cathode gets heated sufficiently up, it will start emitting electrons. These electrons will start traveling towards the anode. The anode is used to focus the beam of the electron, and the beam of the electron over here is allowed to pass over the slow wave structure. Now here whatever you observe, coil-like structure over here is nothing but the slow wave structure. So here it is written. So it is a slow wave structure. Okay. Now this slow wave structure is purposely kept in between the path of an electron beam. The RF microwave input signal which we want to amplify is given as an input signal to one of the port which is placed at this glass tube. Okay, so this microwave signal when injected over the slow wave structure, it will start propagating in the axial direction in this way. Okay, and this will give the axial electric field. Okay, so this axial electric field is developed because we inject the microwave signal over the slow wave structure, and this axial electric field will continuously interact with the DC electron beam. Okay, and as we know that the microwave signal is continuously fluctuating, it will cause acceleration and deceleration of the electrons in the electron beam. And over the period of time, when the electron beam and the axial electric field because of the microwave signal reaches at the output port, we will find that at the output port the microwave signal is amplified in nature. Okay, so this is how the amplification of the microwave signal will take place by using a traveling wave tube amplifier. Now let us look into the details of what do we mean by a slow wave structure. Now please remember, a slow wave structure is an essential and very important component of traveling wave tube. Without using slow wave structure, the traveling wave tube cannot work as an amplifying device. Okay, so here the purpose of using the slow wave structure is to slow down the propagation speed of the electrons. Now a question may arise, why we want to slow down the propagation speed of an electron. See, when the electrons gets emitted by the cathode, what we want is the energy from these electrons we want to provide to our field which we want to amplify, that is in our case that is a microwave signal. So here what we need is we want a certain mechanism with which we can slow down the propagating velocity or the speed of the electron such that the bunching of the electron will take place over a certain length of distance. When the bunching of the electron will take place over the certain length of the distance, so at that time we will adjust the phase of the microwave signal such that the all bunch of electrons will give up their energy to the microwave signal, and thus the microwave signal upon absorbing this energy from the bunch of electron will appear to be amplified, right? So this slow wave structure is a very basic and essential component of the traveling wave tube. So some of the slow wave structure geometrical possibilities are shown over here. This slow wave structure is essentially a coil-like structure. Okay, so here the first example is we can make use of a helical spring-like structure over here. So where we can take a coil or a wire and we can wound that wire to form a coil-like structure or a spring-like structure. Sometimes the helical or slow wave structure can be replaced by a folded back line in this way. So this structure also we can make use as a slow wave structure, or in some cases a zigzag transmission line which is bent in a triangular form can also be used as a slow wave structures. Okay, so the slow wave structures are the special circuits. They are made from the pieces of a transmission line, and they are used to reduce the wave velocity in a certain direction, so that the electron beam, see here the purpose is very clear. Why we are going to make use of a slow wave structure is that we are going to make use of slow wave structure in order to reduce the his wave velocity in a certain direction, so that the electron beam and microwave signal can interact for more amount of time. So this is the only reason why we are going to make use of this slow wave structure, and hence the name is called as a slow wave structure, because we want to slow down the propagation of electron beam with a microwave signal. And if we are able to do that, the maximum interaction is directly inferred from this particular mechanism. So if we are able to slow down the propagation velocity of electron, maximum amount of interaction of the electron beam will take place with a microwave signal. And when this particular thing happens, there is a large amount of bunching that will take place, and from this bunching process we can extract more amount of energy, and we can impart that energy to our microwave signal, which will appear amplified at the output. Okay, so for example illustration, a slow wave structure is shown here in the form of a simple spring like coil. So this is a slow wave structure, and essentially it is a spring like structure. Slow wave spring structure, I can write. So here it is shown. Now this spring like structure has a certain length, okay, and this spring like structure has a certain diameter also, and the number of turns is going to decide what is a typical pitch that is maintained between each turn of the helical structure. So here the dimension of the slow wave structure is specified in terms of certain geometrical parameters. So these geometrical parameters are pitch of the helix, with which we can design the helix traveling wave tube, and small d is nothing but the diameter of the helix. Okay, so here if we take the ratio of phase velocity to the propagation speed, this we can write in terms of these geometrical parameters of the slow wave structure. So this can be simply given as pitch divided by square of the pitch plus pi d square, and this is equal to sine of psi, where psi is the pitch angle, right, and Vp is the phase velocity. Okay, so this is the basic building block of any particular traveling wave tube, and this is how it is actually acting. It is shown over here. So this whatever this red highlighted beam is there, so this is an electron beam. Okay, so in the path of an electron beam, what we do is we will place our slow wave structure. So here is their slow wave structure. Now this slow wave structure is placed in the path of an electron beam, and over this slow wave structure what we do is we will introduce our microwave signal from here. Okay, so when the microwave signal starts traveling over the slow wave structure, it will induce the axial electric field in this way. So this is axial electric field. Now this axial electric field, which is developed because of the traveling of the microwave signal, will start interacting with this electron beam. Okay, and over this entire length of the slow wave structure, bunching operation of the electron will take place. Bunching operation. Now this is what it is shown over here in the below diagram. Okay, so the microwave signal and induced axial electric field, which is shown here with a green color. Okay, and how actually the bunching of electron will take place, it is shown in a more detail over here in this diagram. Okay, so initially these red dots, these are indicative of electrons of an electron beam. When they enter the slow wave structure, okay, so slowly they will start getting accumulated. Okay, so as there is a presence of a microwave signal which is passed over to this slow wave structure, this particular microwave signal will start accelerating and deaccelerating these electrons, right, and over the entire length of the slow wave structure, towards the end, if we find that all the electrons will get accumulated towards the end of the slow wave structure, and at that time we will adjust the phase of the microwave signal as going negative. So whatever, all these electrons are collected together over here and they will form a large bunch. We call it as a bunching effect over there. And when this bunching will observe that the signal is going negative, that especially the microwave signal, all these electrons will give up their energy, and this energy is utilized in order to amplify the microwave signal. And when we take out this microwave signal from the output port, it will appear amplified in the form, and thus we say that the amplification is achieved. So the same is explained over here. The applied microwave signal, it propagates around the turns of slow wave structure. The electron beam, so here I will highlight the applied microwave signal as it propagates around the slow wave structure. The electron beam is focused with the constant magnetic field, which is right now it is not shown in the diagram, but it is there, but so that the slow wave structure. So the microwave signal, as it is propagating over the helical part, it induces axial electric field at the center of the helix, which is directed along the axis. So this is a very important concept over here. This I will underline. So the microwave signal which is propagating over the helix, it will induce an axial electric field at the center of the helix, which is directed along its axis. The propagation of the axial electric field is very close to the propagation speed of light multiplied by the ratio of helix pitch to circumference. So this is also an important statement. When the axial electric field is starting propagating over the length, the speed with which it propagates is proportional to the speed of light multiplied by the ratio of helix pitch to its circumference. When the electron enters the helix, interaction takes place. So essentially whatever I discussed, the same is given explanation over here. So when the electron enters the helical region, interaction takes place between the electron and the moving axial electric field. On average, the electron will transfer their energy to the wave on the helix, and this interaction causes the signal on the helix to become larger. So here, this is a very important statement. As we pass on forward on this helical structure, continuous interaction of the electron will take place with the axial electric field, which is generated because of the microwave injected signal. So the electrons entering at the helix at the accelerating field will get accelerated, and during the retarding field they will get deaccelerated. And as electrons travel further along the axis of the traveling wave tube, they will start getting collected, or we would say that the bunches are going to be formed towards the end of the collector. The bunching process essentially shifts the phase of the amplified signal. Okay, so due to the bunching effect, whatever the amplified signal that we are going to get at the end of the tube, the phase of this amplified micro signal will get reversed by 180 degree. The energy of the entire bunch of the electron will get transferred to the micro signal, and thus we say the amplification is obtained. Okay, so let us discuss about what are the important characteristics of this traveling wave tube. So the operating frequency range of this traveling wave tube as an amplifier is from 3 GHz to any higher particular frequency. Now here the typical bandwidth associated with the amplification operation is around 800 MHz, while the efficiency is a little bit towards the downside, and we will get around 20 to 40% efficiency in the overall amplification operation. And the typical output power exhibited by the amplification process, that will be up to tens of kilowatts, and essentially the power gain, and that's why these are very popular. The power gain of traveling wave tube amplifier can be achieved up to 60 dB, that is a power gain. And coming to the applications of a traveling wave tube, so where typically these traveling wave tube amplifiers are utilized. So these are actually utilized as a low noise amplifier in microwave receivers. They are used in wideband communication links and in coaxial cable repeater amplifiers. And one more typical usage of traveling wave tube amplifier is they are essentially used as a power amplifier in satellite communication. As we know that the traveling wave tube amplifiers are linearly constructed, and as they are non-resonant in nature, they will provide much more advantages over the two cavity klystron amplifier. Okay, so two cavity klystron amplifier, when we compare with the traveling wave tube, it is a little bit bulky and heavier in operation. So that's why traveling wave tube amplifiers will find their application in satellite communication as the amplifying device because of lightweight and less bulkiness. Traveling wave tube amplifiers can be also be used in a pulse aurora. Okay, so let us see some of the gain characteristics of this traveling wave tube amplifier. Okay, so the analysis of actual traveling wave tube amplifier by making use of a field theory is a very complicated mathematical technique, right? So here the power gain is given by this particular equation. The power gain or the gain provided by traveling wave tube amplifier is given by this particular equation, where power gain AP is equal to minus 9.54 plus 4.73 multiplied by n into C. Now here the first term over here, minus 9.54, it is a negative term, and it will decrease the overall power gain. Now why this negative power gain is encountered? Now this will represent the loss parameter. Okay, this represents the loss parameter. Now the losses are going to take place because of the fact that the input signal that we provide for the amplification, input wave, gets divided actually into three different waves. Get divided into three different waves during the operation. And only one of that component, only one of three waves is actually amplified. Okay, so I will elaborate you this concept. So why this first parameter is minus 9.54? The minus 9.54, it indicates that it represents actually the loss in the operation of gain. Okay, so this loss is happening because the input wave, that the microwave signal that we give as an input signal, that will get divided into three waves, okay, with equal magnitude, and out of these three waves only one of the wave will get amplified, right? So that's why this loss factor we need to take into the account while the calculation of power gain of the traveling wave tube amplifier. Capital N over here is the circuit length. Okay, so N is the length of the interaction region. So N we can also call it as a length of interaction region. I write over here, or we can also call it as a circuit length or length of the interaction region. And actually N is actually given by the distance L divided by lambda E, where L is nothing but the length of the slow wave structure, actual physical length of slow wave structure. Alright, and what is lambda E? The lambda E is the wavelength, which is given by lambda E is equal to 2 pi p, v is a velocity, divided by omega. Okay, so where this DC velocity is given by electron DC velocity 2ev0 by m. Okay, so here N is the interaction length of the region, which is given by the ratio of length of the slow wave structure divided by operating wavelength, and this operating wavelength in the denominator is given by 2 pi v upon omega, where v is the DC velocity of electron beam, right? Okay, So when we calculate these dimensions, the numerator and the denominator in terms of meter, actually the circuit length will become a dimensionless. So that's why n represents a dimensionless parameter. The next part is C, capital C. Now this capital C indicates the gain parameter of the entire circuit, which is given by this particular equation. So whenever we want to design the traveling wave tube amplifier, we need to calculate the gain parameter of this traveling wave tube amplifier and the circuit length. So normally the circuit length will be specified in the problem statement, and we will be supplied with the operating DC voltage and the generator current and the characteristic impedance of the helix. So Z0 here represent the characteristic impedance of the helical slow wave structure. Once we have been supplied with all this parameter, we can calculate the gain provided by this slow wave structure. And once we know the gain provided by this structure, we can put down all these values and we can calculate the power gain using the above equation, right? So this is all about the gain characteristics of the traveling wave tube amplifier. Now the next thing is over here that the peak output power of the single helical structure is only limited to around 3 kilowatts of power, because it is very difficult in removing the heat component which is taking place because of the ohmic loss in the coil of the slow wave structure. Now if we apply low input power signal or the small signal, where we can almost gain is assumed to be almost a constant, the RF power input, when we increase the RF input power for the amplification, the RF output power will not increase in the same proportion. But what will happen is it will instead it will attain its maximum amplitude, and then it will start finally decreasing from that particular point. And this particular point at which, with increase in RF input power, the RF output power will start decreasing, we call it as a saturation point of traveling wave tube amplifier, right? So here, as we discussed earlier, the applications of a traveling wave tube. Traveling wave tube in general, they are used in medium power satellite and high power satellite transponder outputs, okay? And traveling wave tubes are the best choice over using two cavity klystron amplifier, as we already said that it is a linear in structure and it is a non-resonant circuit. So that's why they will provide less bulkiness, and this is the typical feature which is very much required in this satellite communication. So this is all about the working principle of traveling wave tube, the important components of the traveling wave tube, that is the slow wave structure, and the geometry associated with the slow wave structure, how the amplification of the micro signal take place, and what are the different important gain parameters of this traveling wave tube, along with the applications and typical parameters exhibited by traveling wave tube amplifier, right? Now we'll spend some more time and let us see one small derivation in which we will calculate the velocity modulation of an electron beam that is taking place inside a traveling wave tube amplifier, right? So we'll go through that particular derivation quickly. I will open a new note and here I will start deriving the derivation. So this derivation is for finding the velocity modulation component of the electron beam which is taking place in a traveling wave tube. So here I will give the heading of the derivation, velocity modulated or velocity modulation of an electron beam in traveling wave tube amplifier. In short, I will write as TWTA. Okay, so velocity modulation of an electron beam in traveling wave tube amplifier. So what we want to derive is a mathematical relation which will show how the electron beam in traveling wave tube amplifier is getting velocity modulated, right? So what we can do is we can write the axial electric field equation which is propagating in the axial direction in the traveling wave tube amplifier. So here I will write the axial electric field. First of all, we need to start with axial electric field. This axial electric field is set up by the microwave signal when we introduce it into the slow wave structure. The axial electric field in the propagation direction is given by, okay, so the electric field, we normally consider that this electric field, propagating field, is traveling towards the z component or in towards the z direction. So this can be written as the components oriented along the z direction. The electric field Ez is equal to, let us say, certain magnitude indicated with E1 sine of omega t minus phi of z. Let us call this an equation number 1. So this is a generalized equation of axial electric field which is directed along the axial direction of traveling wave structure. Okay, so where E1 is, this is a magnitude. So this is the magnitude of that axial electric field. And what is phi? Phi indicates the axial direction phase constant. So phi is axial field phase constant. Okay, so this phase constant can be written as omega divided by phase velocity Vp, where Vp is phase velocity of the wave or of the signal, right? So a force will be exerted. So here I will write, when the axial electric field is generated along the direction of slow wave structure, this axial electric field will exert a force on the electrons of the electron beam. So here I write this axial electric field will exert a force on the electron beam. Now how this force is given, which is exerted by this axial electric field on the electron beam? We know the classical equation, force is equal to mass into acceleration. Okay, so this can be written as mass multiplied by acceleration is dv by dt, rate of change of velocity with respect to time. We can write in this way, and this can be equated to minus e times Ez. Okay, and when we substitute the value of Ez from equation number 1, we can write minus e, and Ez can be replaced as E1 sine of omega t minus phi of z. Okay, so let us call this an equation number 2. Okay, so here I will write the total velocity of electron. Okay, so how we can write the total velocity of electron? Total velocity of electron can be divided into two parts. So the total velocity of electron means the total velocity of electrons in the electron beam. So the total velocity of electrons can be divided into two parts, and this can be given as original DC electron velocity. This is equal to original DC electron velocity, right? which was the original velocity when the electrons get released by the cathode, plus there is a velocity component, plus the velocity component due to velocity modulation. Due to velocity modulation operation. Okay, so we are interested to find out this particular component. Okay, so which one? We are interested to find out what is the velocity component because of the velocity modulation operation. Okay, and for which we are deriving this particular derivation. So this total velocity, how it is then given? So this total velocity, let us denote it with capital letter V, is equal to the DC electron velocity V0 plus, let us say, the modulated velocity of electrons because of the velocity modulation process, and let us denote it with VE cos of omega ET plus theta E. So I will write again. So cos of omega ET plus theta of E. Let us call this an equation number 3. So in equation number 3, the first part over here, okay, so this indicates the original DC velocity. Original DC electron velocity. While this second part of the velocity is due to velocity modulation. This component of velocity is due to velocity modulation that is taking place over the length of helix. Okay, so what we do is we substitute equation 3. Now here I will write substituting equation 3 into equation 2 above. So you substitute equation number 3 into equation number 2. Okay, so what we can write then? So equation 2 is force. Okay, so force we can write m dv by dt, right? So this m dv by dt, where we can replace with the equation number 3. So here m d by dt of v, or d by dt of v, that I will take from equation number 3, v0 plus ve cos of omega et plus theta e, bracket complete and bracket complete, right? So if we simplify, if we take the derivative inside this particular bracket, we will write minus e1 sine of, when we simplify that, omega et minus phi of z. So this can be written on the right hand side over here. So I will rewrite it again. So when you substitute this one, so what is there on the right hand side of equation 2, we will write that as it is. So this is equal to minus e1, right, sine of omega t minus phi z. Okay, now we take derivative on the left hand side, and when we take the derivative, we can directly write minus m ve sine of omega et plus theta e into omega e, bracket complete, is equal to minus e1 on the right hand side, sine of omega t minus phi z. Okay, so we can write by removing the negative sign on the both side and rearranging the terms. We can write this equation as m into omega e into ve sine of omega et plus theta e. This can be written as e into e1, right? Sine of omega t minus phi z. Let us call this an equation number 4. Okay. So after this we will simplify it further. Okay. So for the proper interaction that whenever we want to take place between the electron and the electric axial field, the velocity of velocity modulated electron beam is approximately equal to the DC electron beam velocity. So here we assume that for, I will write that condition, for proper interaction between axial electric field with electrons, the necessary condition is the DC electron velocity must be approximately same as that of velocity of modulated beam or modulated electron beam. See here, what we are assuming is that we already saw that the total electron beam is divided into two components, which is specified by equation number 3 over here, where we consider the first part to be original DC electron velocity and second part is the velocity component which is happening because of the velocity modulation process. Now in order to effectively take place the complete interaction, we should assume that both of these velocities are going to be same. So here what we can assume is, so v is equal to v0. Let us call this an equation number 5. Okay, and the distance over which the interaction is taking place is given as a z along the z direction, and this can be written as velocity into time, and this time is t minus t0. Let us call this. Okay, so what we do is we substitute equation number 6 into equation number 4. So here in terms of z over here, substitute equation 6 into equation 4. Substituting equation 6 into equation 4, so what we get, equation number 4 then, so we get m multiplied by omega e into ve into sine of omega et plus theta e, right, is equal to e into e1 sine of, okay, so here into bracket omega t minus phi. Now here I will replace the z with the component v0 into t minus t0 from equation number 6. Okay, so this can be written as m times omega e ve sine of omega et plus theta e. This can be written on the right hand side as e into e1, right, into sine into bracket. We can have the multiplication, so we can write omega minus phi v0. We can take the t common outside over here, plus phi v0 into t0. We can write in this way. Okay, so let us call this as an equation number 7. Okay, so we know that the phase constant, now here the phase constant is a phi. This phase constant is the phase of the axial electric field. So this phase constant phi is given by omega divided by phase velocity Vp. Therefore, omega can be written as phi multiplied by Vp. Okay, so here on the left hand side, m times omega e Ve sine of omega et plus theta e, this can be written as e of e1, right, into sine component of into bracket. Now here what we can do is we can replace omega with the term phi into Vp. Okay, so here when we replace omega with phi, Vp minus phi of V0 into t plus phi V0 into t0, right, bracket complete. So what we simplify, the next m omega e Ve, further we simplify sine of omega et plus theta e. Now on the right hand side from the bracket term we can take out the phi term as a common. So sine into bracket, if we take out the phi term over here, inside of this bracket we left with Vp minus V0 of t, right, plus phi of V0 into t0. Now let us call this an equation number 8. Okay, so if we compare both sides of equation number 8, so here I will write comparing both sides of equation 8. When we compare both sides of equation number 8, we can write the terms. So I will highlight that term. So this particular term m omega e Ve can be considered as a E1. So that we can write. So m into omega e into Ve, that can be equated with the right hand side equivalent term E into E1, right? So from this we can find out what is the component of velocity modulated electron beam. That is, we are interested to find out the expression for this particular component Ve. Okay, so this can give us Ve, okay, so is equal to E1 divided by m times omega e, right? So let us call this an equation number 9. Okay, so here what we can write then, omega e, then it can be written as phi times Vp minus V0, right? This is say equation number 10, and Ve can be written as, this can be written as E of E1 divided by, so here I will make the change, E of E1 divided by m, right? So here we can replace this with pi Vp minus V0, or this can be also written as phi V0 into T0, right? So here, rather this particular equation, we'll remove this, and here Ve can be written as E1 divided by m omega e, okay, where omega e can be considered as a t term Okay, so when we compare this particular term over here we consider the omega e, which is multiplied with the t. Omega e is 5 times Vp minus V0. Okay, and this particular term theta e, when we compare both sides, theta e can be given as theta e is 5 times V0 into T0, and let us call this an equation number 11. So equation number 9 and 10 and 11 we will get when we compare both sides of equation number 8. Okay, so what equation number 9 indicates over here? Equation number 9 is of particular interest for us because VE, equation number 9, it indicates, so this is the velocity modulated component, velocity modulated component of an electron beam. So what we notice here, equation number 9 is nothing but the velocity modulated component of the electron beam. So here we started the velocity modulation of an electron beam. So the equation number 9 essentially indicates that this is the velocity modulated component of the electron beam. And if you see on the right hand side, the velocity modulated component of the electron beam is directly proportional to the magnitude of the electric axial field. Okay, so that is E. Okay, so here we can conclude that the more is the magnitude of axial electric field, more is the velocity modulated component of the electron beam in the total equation of velocity modulation. So the total equation of the velocity modulation is given by equation number 3, and the second contribution made by the velocity modulation will tend to increase with increase in the magnitude of axial electric field, right? So in the case of traveling wave tube amplifier, one type of electronic equation or the convection current equation is normally expressed. Okay, so directly this convection current equation, which is in terms of the field component E1. So what is E1 over here? So here E1 we considered to be the magnitude of the axial electric field. Okay, so this E1, the magnitude of axial electric field, how it is going to generate the convection current. Okay, so the convection current over here, I will directly write the equation for the convection current in traveling wave tube. Okay, so the convection current, see why it is called as a convection current, because this current is not a direct DC electric current, but this current is developed because of the space charge effect which is generated by the continuous interaction of axial electric field with a beam of an electron. And this current which is gets generated and which is responsible for the amplification process in a traveling wave tube, we call it as a convection current. And the equation of that convection current in traveling wave tube is given as I is equal to, it is an imaginary term actually, so J times E divided by m square of DC electron velocity beta E phase shift times magnitude of the current, we can replace J beta E minus gamma whole square times E1. Okay, so this particular equation is the equation of the convection current. Now on the right hand side, if you observe, that is, it is a purely imaginary current. Okay, and this current is not a physical electric current, but this is a current because of the space charge effect that is getting created because of the continuous interaction of axial electric field with the electron beam. Okay, and this equation denotes that this convection current is proportional to the magnitude of the axial electric field. Okay, so this particular equation number 12 is sometimes also called as the electronic equation of traveling wave tube. Electronic equation of traveling wave tube. Okay, so convection current, please remember here the J term is involved. That means it is an imaginary current, and it always depends on the magnitude of axial electric field. So in the traveling wave tube amplifier, this particular current is a convection current, and this induces electric field in the slow wave structure. Okay, and this equation of the convection current is popularly known as electronic equation of traveling wave tube. Okay, so I hope you understood the principle of working operation of a traveling wave tube amplifier, all its operation, the velocity modulation process, the application, and the details of slow wave structure and a derivation to find the velocity component which is taking place because of velocity modulation effect in the traveling wave tube. And finally we saw the equation for convection current, which is popularly known as electronic equation of a traveling wave tube amplifier. So thank you very much. We stop over here.